So what's the unit of the set of complex numbers, group of complex numbers? Well, it's just 1, right? 1. So so the kernel is all possible values of x here of this form, where this equals 1, right? So here, it's the set of all these elements. Where each of the 2 pi I x equals 1. Well, you probably know that e to the 2 pi I is 1, right? Plus 1. Why? Because, well, e to the pi I, you know, that famous formula of Euler, Leonard Euler, or Leonard. He was Swiss. I wonder if he was French-Swiss, in which case his name was probably, if I pronounce it in French, would be Leonard Euler. I don't know, Euler, very German sounding name. Leonard, I don't know. French are such polyglots. He may have a personal name that's French and a family name that's German. Doesn't. That's the Swiss. Okay. Alright, so so you got e to the 2 pi I x has got to be 1. So that puts restrictions on what values x can have, and in fact x has to be an integer. Can you see that? Because e to the 2 pi I is 1. And this is a complex number, and so x has to be an integer. So the kernel is a set of all integers. Well, that's just z, right? Z is z, big Z, capital Z, is just the symbol for the set of integers. Right? So we know the kernel is just z. It just means all the integers, right? How about the image? The image. So it's the set of all possible values for f of x, right? On the right hand side, that your group H, your map, that you're mapping onto. So each member of your image of f will have this form. Now that's any old complex number, except that its modulus, you know, its size, has to be equal to 1. Right? You can see this. So the size of f of x, it's of this form. So if I take the modulus of f, you know, what's its absolute value, take the mod of that, I'll get 1. There's no number outside here. It's just exponential or something. So if I mod it, I'll just get 1. So mod of fx is 1. Right? So your image, you know, the set of all possible different f's, are just all the complex numbers that have a modulus equal to 1, right? Let's call that set T. Right? So T is the set of all complex numbers with modulus, or in other words, size, equal to 1. In other words, those complex numbers lie on the unit circle in you know, complex number space, Z, little z, complex number space. So here's your unit circle, right? Y-axis, x-axis. The Argand diagram, if you've done enough complex number theory, right? So the set T are all those numbers, complex numbers, that lie on the unit circle with radius 1. Okay? So we know the kernel is the integers, set of integers. We know the image is T. That's all the points lying on the unit circle. The original group is just the reals, right? So that's your big G in a sense. So so we know the kernel, it's Z, so plug it in here. We know the image of f is T, that's the complex numbers that lie in the unit circle, plug it in here. So here we have our third relation, our third example of first isomorphism theorem in this form. Okay, so there's a bit of a comment here from the text. If you're multiplying two complex numbers that have a unit modulus, meaning their size is the absolute size of the complex number is 1, and if you have two of them like that and you're multiplying them, that's sort of equivalent to adding angles at the center of your unit circle. Okay? So if you have two numbers like that, you can get the result by adding their angles. Like, well, I'll just draw it. Here's your Argand space. Here's a unit circle, and let's say this is one point on your unit circle here, and you've got another one here. So you'll have an angle here, θ1. You'll have another one, an angle θ2, and when you multiply those two numbers, the result you'll get will be, it's over here somewhere, with whose angle will correspond to θ1 plus θ2. Okay, that's all it's the same. All right. Fourth example. What are you doing? You're mapping the integers to a group. That's interesting. It's a bit unusual. Here, your group G is the target. Usually, big G is the starting group. So, pay attention. All right. So, what is the mapping? So, we're mapping integers into a group somehow, and here's how it's done in detail. So, here's the mapping at the level of elements of these two groups. So, you take an integer n that belongs to Z. Okay. And you map n into a of n. And what's this little a here? Well, a is just any member of some group G, quite general. You've got a group G, and a is just some random, if you like, member of that group G. So you just raise that element, little a, to the nth power, this integer. Right? So once again, that mapping, that f, is it homomorphic? Well, binary operation here is plus, so f n m will be f n plus n plus m, or m plus n, doesn't really matter in this case. Right? So that is a to the n plus m, just using this definition. Okay. Now you can split, these are just exponents, so you can separate them, split them up, so you get a to the n times a to the m, but a to the n is f of n by definition, and a to the m is just f of m, right? So therefore this equals this, so we've just shown that f is homomorphic, right? Okay, now as usual, find the kernel and find the image of f, and once you have those, just plug them in here and here and write out the formula of this form, showing the isomorphism between the groups on the left and the group on the right. The group on the left is always a quotient group, but I haven't said that explicitly before, but that's pretty obvious from the context. Okay, so what is the image of f in this case? The image. It's all possible value, the set of all possible different values of f. Right? Now look, this a here is an element of a group G. It's an element. Elements have orders. Right? Now the maximum value, the maximum order this element A can have will depend on the nature of G. So if well, it depends on little a as well. Okay, we're talking. Yeah. Again, remember the distinction between the order of an element and the order of a group. So have a look at this element. and ask what's its order, right? Now if it has infinite order, there's no finite n such that a to the n equals the unit of the group of G. Okay? So if it has infinite order, then I'll go way back to theorem 18, then the kernel is just the 0. There's only one value that maps to E, and that's when this n here is 0. Because remember, any element to power 0 is the unit. Okay? So if there's no finite n that gives you a to the n equals E, in other words, that has infinite order, then there's only one little n, integer n, that gives you E, and that's 0, right? So therefore, we're talking about the kernel. Where are we? Then so then the kernel is just 0. It's just a set with one element in it, 0. Just one integer. And that comes from theorem 18. So if you're a bit rusty on that, why that's the case, go back and have a look. Okay, now assume that this element now is of finite order, all right? And let's say its order is n, the integer n. Then so we're trying to find the kernel, right? Kernel is a subset, set of all values